Hello everyone. So today we are going to be talking about gravitational potential energy. So let's say that you have an object and you lift it some height above the surface of the Earth. If you released this object, we know that it would fall to the Earth. What actually caused the object to move from this point to this point was the fact that it had gravitational potential energy while it was above the surface. That's what we're going to talk about today, diving into this a little bit more. So we know about work. Work is equal to force times a displacement. So you need to have a force that's operating over some distance in order to have work. Now in this case, the displacement is just the distance above the height of the Earth. So what about the force? Well, the force here is going to be the force due to gravity. Now, thanks to a fellow called Newton, we know the equation for this force is equal to negative the gravitational constant times the mass of the central body times the mass of the object divided by the distance between the two objects squared. Big M here is just going to be the mass of the Earth. And r here is actually just the radius of the Earth, because the distance between the two objects is the distance between their center of masses. And basically the distance between the surface of the Earth and the object is going to be negligible. Now, in fact, this particular combination of the universal gravitational constant, the mass of the Earth, and the radius of the Earth squared is used so often that we actually call this its own constant, which we call little g, which is just the acceleration due to gravity at the surface of the Earth. And so because all of these things are constant, g has a constant value, which is just 9.8 meters per second squared. And meters per second squared is a unit of acceleration, which makes sense because I said that this was an acceleration. And now if we go back to Newton again, we know by Newton's second law that force equals mass times acceleration. And we said down here that force is equal to this times the mass of your object, and so A equals G, and so A is an acceleration, G is an acceleration, it matches up. This negative sign here just means that the force of gravity is attractive, so it's bringing the two objects together. So if we go back to our work equation, force times displacement, we said the displacement is the height, and then the force is the mass times the acceleration, so that's going to be m times little g. So we know that this work is equal to mgh. So if an object is starting here at some height h, we know that if we drop it, force of gravity is going to do work on it to bring it down to the surface of the Earth. And so we can say that the potential energy stored in this object, or the gravitational potential energy, is just equal to that amount of work that's going to be done, which is mgh. So that is the capacity for work to be done on this object by gravity. So let's do an example. So let's say that you have a cliff diver who's standing on a 10-meter tall cliff, and she weighs about 75 kilograms. So as she is standing here at the top of this cliff, what is her gravitational potential energy? Okay, well, we can use this equation that we just derived, and we know that her mass is 75 kilograms. We know that g is 9.8 meters per second squared, and we know that h is 10 meters. Now, if you multiply all of these together, you get 7,350. And the unit here is kilogram meters squared per second squared, which is kind of a mouthful, so there's actually a separate unit that we use for that is equivalent and is just called a joule. So 7,350 joules is her gravitational potential energy standing at the top of the cliff. Now let's say that our cliff jumper here has decided to take the plunge and she's going to jump off the cliff. When she reaches the water, what is her gravitational potential energy going to be? Well, we can use this again, but now she's actually at the surface of the Earth, right? Sea level is going to be at the surface of the Earth, so her height is 0 meters. So now she actually has 0 gravitational potential energy. So what happened to all of that gravitational potential energy that she had at the top? Well, we said that was the capacity of gravity to do work on her, and so the work was done on her, and work equals the change in kinetic energy, and so her kinetic energy then must have changed from the top to the bottom. Knowing this, we can actually calculate her speed as she enters the water. So we know that her kinetic energy at the bottom must be equal to what her potential energy was at the top. And we also know that kinetic energy is equal to 1/2 mv squared. So we can actually solve for what her velocity is as she enters the water. So the m's will cancel out, and if you rearrange this, you end up with the square root of 2gh equals her speed entering the water. And notice that your units will work here, right? You'll have meters squared per second squared and then take a square root, so you'll end up with meters per second. And in this case, it is 14 meters per second. Okay, now say that her brother is also with her, and he's standing at the top of the cliff, and he has a mass of 100 kilograms. So we can do the same thing for him. In this case, it is going to be 100 kilograms times 9.8 meters per second squared times 10 meters. And this ends up being 9,800 joules. So he has slightly more gravitational potential energy because he has a higher mass. And again, we know that entering the water, he will have a gravitational potential energy of 0, and all of his previous gravitational potential energy will have been converted into kinetic energy. Because we already solved for the velocity equation, which, if you'll remember, was the square root of 2gh, we can again solve for his velocity entering the water, and we'll find 14 meters per second. Now, does that sound familiar? He actually enters the water with the same speed that his sister did. And this is because the final velocity does not depend on mass. There is no mass dependence, because remember, those masses canceled out. So even though he has more gravitational potential energy at the top of the cliff, he achieves the same speed. If you look at actual data, so from a paper that was published in 2020, they took actual data of divers entering the water, which you can see here in a camera they set up, and they also measured their speed. And so right here, this is on the this is showing the time after they hit the water. So at 0 was right when they hit the water, and the axis here is the speed, and you can actually see that coming from a 10-meter diving platform, they actually hit the water at just about 14 meters per second. So I'm not lying to you. Okay, so today we talked about gravitational potential energy. We found an expression for it, which is equal to mgh, where m is an object's mass, g is the acceleration due to gravity, and h is the height above the Earth's surface. We learned that this gravitational potential energy is the capacity for gravity to do work on an object. And we learned that this gravitational potential energy can be converted to kinetic energy. And we did some sample calculations. Thanks for watching, and I hope you learned a little bit of something.